All right. Good evening, everyone. So probably we will start now. Thank you, Avinash and Krishna Kumar for joining. Today we will be today. This is our fifth week of problem solving session, and we'll be addressing fifth week's content, which is going to be 2D steady state uh, heat conduction equation, and also we touched transient heat conduction equations. Um, so um, Before we get into today's class, if you have any questions, please let me know. I can quickly address them. Okay, I think there are no questions. No problem. So today we'll be solving one question actually, which is going to be on transient heat transfer. This is because 2D steady state problem, it's not easy to do by hand. Usually we use computers to do it, and we use finite element method or finite difference method to solve 2D uh, heat conduction problems. So that's why we gave an idea during the class, and we will not be going forward in that direction. And also, it's more mathematically involved rather than some physical interesting insights that you can get out of it. Um, Otherwise, transient heat analysis something you need to know before, as part of uh, what do you call, a fundamental heat transfer course. So, and that's why I think in your class, in your assignments too, there are mostly transient heat transfer analysis questions. So let's just quickly go through what we did in week 5. So in week 5, most of the time, we spent on 2D steady state heat conduction equation, if you remember. So till now we have been dealing with 1D steady state heat conduction. Now we've started doing 2D steady state heat conduction analysis, and we understood when you should say it's a 2D problem and when it is a 1D problem, and how you simplify a 2D to 1D problem. All these things professor has discussed, right? And finally you will end up having this equation called Laplace equation, and you will see this kind of equation in various other uh, other subjects too, like um, this is one place where you will have this Laplace equation. Sometimes instead of 0 you will have some source terms or some functions, then it becomes a Poisson equation, and various physical phenomena can be modeled using these sets of partial differential equations. These are all called partial differential equations. Okay, and if you have such a Laplace equation, then there are few methods to solve it. You cannot simply integrate it as we integrate for a 1D problem, um, because you have two independent variable here, both x and y. So that's why we have some separate special methodologies called method of separation of variables. And there are few conditions that you need to satisfy. One is it should have homogeneous boundary condition, and also it should be the equation should be homogeneous. So that is what you see here. And then you assume that this is how the solution looks like. It is a function of one independent variable times the function of other independent variable, f of x times g of y. Okay, and then if this is the solution, you substitute in this equation and you end up getting this kinds of uh, relation, and at the end you will reduce this into uh, what do you call a 1D uh, you know a differential equation with one independent variable. So for example, this f double dash f time equal to minus lambda square has only one independent variable, which can be easily integrated. Similarly, g double dash by g equal to minus lambda square. Here lambda square is constant. Then it becomes one independent variable which you can integrate it. Once you integrate it, you will get the functions. you multiply those two functions, you will end up having the full solution to your 2D Laplace equation. Okay, and you apply boundary conditions to find the C's, and you will end up having eigenvalue problem, and then which means you will have multiple solutions, right? And for different n you have different solution, which means a summation of all these is also a solution. So that's why we write it as a linear combination of all these solutions together, summation. And then you continue doing some more mathematical steps. You come to this orthogonality condition, and then you will end up having your Cn expression of that final constant, and then you substitute this constant in the equation that we in the solution. This is the solution. So we perform some more mathematical steps to find this Cn. Okay, and that it is based on the orthogonality condition, because we used fourth boundary condition for, and then it led to eigenvalue problem. So now we need another condition, which is an orthogonality condition, to close this system, and that's why you have this Cn. And once you have this Cn, you substitute it here, you will end up having the solution to your 2D steady state uh, heat conduction problem. Okay, but usually you will not see this in in any practical applications. You will not have some square or rectangular slab, and you want to see how heat is flowing in between. Usually it's not like that. In practical applications you have more complex geometries, and doing such a analysis for this complex geometry is going to be very difficult. And that's why people usually tend to go towards numerical methods. They use finite difference or finite element, finite volume, all these analysis to solve this partial differential equations. And in general also, 2D is just one step above 1D, but in general problems are in 3D, right? So coming up with this relation for a 3D problem it's near to impossible. Okay, so that's why people go into numerical methods. And if you are interested, you can go through some CFD courses to understand how these kinds of PDEs are solved. Okay, and then yeah, so basically if you have different boundary conditions, how will you solve the problem, method of superposition, all these things is little bit advanced for a fundamental heat transfer course, but we tend to introduce such advanced concepts uh, to increase your curiosity. Okay, that is why we did this. And we also had different boundary conditions. If it's a melting of solid, how it is boundary condition. If it's a freezing, how will you kind of apply a interfacial boundary condition in those places. So basically you need to solve these boundary conditions with the heat conduction equations, then only you will be able to get the final solution. Basically these are boundary conditions. These are boundary conditions. Like we have dt by dx equal to 0, or a heat flux boundary condition. Here you have a melting of solid as a boundary condition. And what you also see is these interfaces continuously tend to move, right? That's why you have this dx by dt, which means the interfacial velocity. So these are called something like moving boundary conditions. So usually you will see only static boundary conditions, where the boundary is fixed over there in space, and there will be heat flux coming in or going out, or temperature, you already know all these things. But here the boundary is moving because of melting. When melting happens, the boundary keeps moving down. When freezing happens, boundary keeps coming up, right? So these are called moving boundary conditions. Anyway, so these are little bit advanced topics in the conduction. And finally, we also studied about unsteady heat conduction or transient heat conduction analysis. In that, the important thing that we studied is lumped parameter approach. We also studied where it is important, and how we will solve. So basically, till now we have did only steady state problems, which means there is this transient term which usually we ignore. So now This is an unsteady heat conduction problem, so we cannot ignore it anymore. We have to include this in the analysis. So, so till now we dealt with steady state, and now we are going to deal with unsteady heat conduction problems. Okay, and this is basically you have a heated ball, or you want to cool down a ball, or a sphere. Uh, um, in a quiescent medium, where air can flow around it, and you will have some heat transfer coefficient. Also, since this sphere can have very high temperature, you can also have radiative heat transfer. So basically the this is just a sphere, and if you apply energy balance, the energy content of this sphere is going to continuously change from t equal to 0 to t equal to, let's say, some steady state. At steady state, uh, if let's say this is the heated sphere, then suddenly if you are exposing it to a cool ambient, then it starts cooling down. The hot sphere starts cooling down. So we are till now, in our previous weeks, we are just interested in at the steady state what happened to the sphere's temperature, sphere's uh, uh, the air's temperature, how it is different, what is the temperature profile within the sphere at the steady state after t equal to, let's say, some big number. Okay. Um, Now we are interested in analyzing from t equal to 0 to the steady state how the temperature varies, how temperature changes with respect to time is what we are interested in. That is what we do in an unsteady heat conduction problem. For example, when we have a heated sphere, how much time does it take to cool down to, let's say, ambient temperature? um, that that kind of analysis, if you want to know, then you have to do an unsteady heat conduction analysis, and you will no longer be neglecting this unsteady part. And the what is, so since it's an heated sphere, there's going to be continuously energy going out of the sphere, and one is through convection and another is through radiation. That's what we did. We had convection and radiation. So for this the special case, we ignored radiation. Let's say radiation is not important and only convection is important. Then we simplified the equation, and then we integrated it with respect to time, and then finally we got this expression, if you remember, during the class. And uh, so this is our final temperature profile with respect to time. You can see this is theta. Theta is nothing but t minus t infinity, and it is a function of time. It is not a function of space. Till now we have been studying steady state conduction with with its function on space. Now we are only studying how it varies with respect to time. Okay, uh, which means with the space it should be uniform, right? So that is uh, one of the important assumptions that we need to make if we are following lumped parameter approach. That is what it means. Lumped parameter approach means there is no variation along the space, or there is minimal variation along the space. Now, how do we know there is minimal variation along the space? That is based on this Biot number calculation. So if the conduction within the sphere, it takes the resistance of, you can say, uh, if the potential for the conduction within the sphere is very high, which means the resistance for conduction within the sphere is very high compared to the convection resistance, then you can say whatever the energy given on the surface, it will be quickly dissipated within the sphere, right? That is what conduction resistance becoming very less means, and that actually corresponds to Biot number very very much less than 1, right? For practical applications, we said Biot number is less than zero point 0.1, which corresponds to conduction resistance being very small compared to the convection resistance, compared to the energy coming from the outside, or energy going to the outside, the resistance to the energy going to the outside. So that is when we can use lumped parameter approach. So when the Biot number is less than zero point 0.1, the whole sphere will be of uniform temperature or near to uniform temperature, which means the Tc and Ts, the center temperature and the surface temperature, will be almost equal. Okay. then this actually corresponds when buyout number is less than 0.1. And if this is the case, then you can safely apply lumped parameter approach, which is exactly the approach that we were talking about. Okay. And then we studied the time constant, which is just the manipulation of the equation. And then you also have Fourier number that we saw. So these, we also saw that it is used in, riser design in a casting process. You want the riser to solidify after uh, all the material inside the mold is solidified, right? That is the whole point of riser. So when material solidifies, it might shrink, and the actual dimensions might change, right? And also, so when these dimensions change, when you have extra space, then you should have enough uh, metal which can go and fill inside it. So that is why we have a riser, and riser will hold some extra metal and liquid molten metal which takes up the remaining spaces. Uh, and if you want that to happen, then the casting, the metal inside the mold, the molten liquid metal that you pour inside the mold should solidify before the riser solidifies. Okay, so if you want to do that, then you have to design a riser such a way that it does not solidify before, which means you need to perform a transient heat conduction analysis, and you need to make sure the time constant of this riser is higher than the material, okay, than uh, the workpiece. Okay. And then we also did this is one lumped parameter approach. And then we also did, let's say lumped parameter is not valid within the sphere, or within the material, the temperature can vary along the space also. Okay, for example, you have 1D, let's say along X it can vary, the temperature can vary, and also with respect to time the temperature can vary. So T will be a function of both space and time, X and T. So in that there are different special cases that you can solve, um, which will give you which can lead to solution, a closed form solution, like we did for 2D Laplace equation. This will also lead to a closed form solution. Okay, so one such thing is infinite slab, where you have infinite slab along the y direction, and you have some thickness, the slab thickness is something like 2L, and you have some initial temperature, and then let's say based on boundary condition you increase the temperature, or let's say you give some heat source into it, then how the temperature initially, which was uniform, how it gets disturbed, and how it forms a final temperature profile is the question that we want to answer. So from initial to the steady state condition, how the temperature within entire within the space, how how it varies with respect to time is what we want to answer. So that will boil down to this kind of equation. And then again, you can perform method of separation of variables, which we did, and then you do the same analysis, you will end up having eigenvalue problem, and then to solve this CN you derive an orthogonality condition, and then you will end up having such the constants will be, you'll be able to find out. And then once you know the constants, then you can substitute this constant in the equation that we have here, and for every x within your process. So this is basically the solution. So once you know the Cn, you basically know everything about the temperature field with respect to both space and time. Okay, that is what it means. So basically, if you give the properties of the material, and if you give the boundary conditions, you can literally find how the temperature evolves at each and every point in the slab with respect to each and every time. That is what the solution here provides. So you will have initially something like this, and then as time increase, you can have something like this. That is what this means. Okay. um Now this is considered for if both the ends are at different temperature. Now similarly, a superposition can apply. You can apply something like, if you have, if both the ends at different T and the temperature is with respect to time, it is varying, then how it will vary. So that is also you can do based on superposition and all. If you are interested, you can go forward and do this. This is an advanced level math. Anyway, uh, this is not currently useful. Uh, this is not you can something do it using your hand by hand. You may need to use computers or programs to uh, predict the temperature. Okay. All right. Um, and so this is what we did in the class. So a little bit of math, a little bit of advanced topics, and also a new topic called transient heat transfer that we did in week 5. Uh, and in your week 5, I think assignment involves this lumped parameter approach to solve problems. So that's why I have one problem. Today I do not have more like 2, 3. I have only one problem. I will show you how you can solve it. I will understand what is this lumped parameter analysis in detail based on this problem. And hopefully it will be helpful for your assignment. Okay. So I hope there is no question. If you have any question, as usual, you can stop me anytime. You can use chats or you can unmute yourself. You're more than welcome to do. You're more than welcome to interact with me however you want. Okay. All right. With that note, let's solve this first problem, or the only problem for today, which is the thermal energy storage systems commonly involve a packed bed of solid space. So this is something to do with thermal energy storage system, and they have a packed bed of solid spheres. So they have some solid spheres, which is you know they they packed inside this system, through which a hot gas flows if the system is being charged, or the cold gas if it is being discharged. So basically, you want to heat something, and you can send a you can use this thermal energy storage system as a heating device. So if the thermal energy storage system is made of this solid sphere, and if the solid spheres are hot, you send the air inside them, which takes away all the hot gases, which gets heated up. The air gets heated up and it comes out as a hot air. That's what it means. So if the cold gas flows, then the system is being discharged to the uh, air. And let's say if the sphere is cooled down and you send the hot gas, so because of hot gases, what happens, the spheres get heated up and it stores a lot of energy at a high temperature, which they say it to be charged. So it's just a naming convention, so no, don't worry about it. Basically you have a packed bed of spheres and you are sending hot gas inside, which means the packed bed is going to take away heat from the hot gas, and the gas coming out of the system is going to be colder. Okay. And if you send cold gas inside, then whatever the sphere, whatever the energy it has, it dissipates it to the gas, and whatever the gas comes out from the system will be uh, hot gas. That's what it means. So in a charging process, which means you are sending a hot gas inside and you are charging all those particles inside, which means you are heating up the particles inside. The heat transfer from hot gases increases thermal energy stored within the colder spheres. During discharge, the stored energy decreases as heat is transferred from warmer spheres to cooler gas. So basically, same thing they are repeating again. Consider a packed bed of 75 diameter aluminum spheres, okay, and with a density, this is actually density, rho, of 2700 kilograms per meter cube, and the specific heat is given, which is 950, and thermal conductivity is given. And the diameter of the sphere is 75 which is also given, and a charging process for which gas enters the storage unit at 300 degrees Celsius, okay. And if the initial temperature of the sphere is 25 degrees Celsius and the convective coefficient is H, how long does it take a sphere near the inlet of the system to accumulate 90% of the maximum possible thermal energy? This is what they are asking. So, and what is the corresponding temperature at the center of the sphere? Okay, so which means now you are sending the gas at 300 degree Celsius and the spheres are at 25 degrees Celsius. So what happens? The sphere gets heated up, and um, if it gets, if if you can store 90% of the energy, how much time does it take to reach that 90%? Okay, how much time should I send the hot gases such that I can heat this entire packed bed system up to 90% of maximum possible energy? Okay, uh, which so how much time does it take is what they're asking. And after that, what will be the temperature of the sphere? So at the end of the, once you store this 90%, once you send hot gases for certain amount of time, it accumulates all the energy and it will correspond to 90% of maximum energy that it can store. And once you reach that uh, point in time, what would be the temperature of these spheres inside? And that is the second question. And is there any advantage to using copper instead of aluminum? So till now these spheres are aluminum. If I change it with copper, do you see any advantage? These are the questions they are asking. Um, you can think about it in a minute. I am going to check something. Uh, Give me a minute. All right. Let me check whether this session is recording or not. All right. I think it is recording. Okay. Anyway, sorry about that. There seemed to be some problem in recording, but yeah, it's fine. So that's the problem is about. We have to find out what is the time it takes to store 90% of maximum thermal energy it can store, and we also need to find what is the temperature. Well, let's just focus on that first. So if, let's say, if I want to draw a sphere, so this is a sphere which is made of aluminum, and this is 75 mm in diameter. Okay, and um, you have gases that is going to flow over this, which is going to be at TGI, which is 300 degrees Celsius, and this guy, the sphere, is in 25 degrees Celsius, and the density of the sphere is 2700 kilograms per meter cube. Cp is 950 joules per kg Kelvin, and the thermal conductivity is 240 watts per meter Kelvin. Now, yeah, the heat transfer coefficient is also given, which is 75 watts per meter square Kelvin. Okay. Yeah. Now you want to find out. So what I need to find number one is time taken to store 90% of maximum thermal energy that can be stored. So first you need to know what is the maximum thermal energy that this can store, and then you need to know, you need to find time for only 90% of that. Okay, maximum thermal energy that can be stored. Okay, So basically you have a sphere with initial temperature 25 degrees Celsius, and you have gases flowing which is at 300 degrees Celsius, and you are going to heat that sphere using those gases. So my question is, what would be the maximum thermal energy that you can store? So if you have a sphere with 25 degrees Celsius and surrounding temperature is 300 degrees Celsius, the maximum thermal energy it can store would be how much? You guys don't need to think this much. So basically it is storing in terms of heat capacity, right? So heat capacity is nothing but the amount of energy it can store per unit mass and for 1 degree change in temperature. So what is the maximum change in temperature that you can have in this system? So initially you have 25 degrees Celsius, your surrounding gas is 300 degrees Celsius, which means you can heat this sphere up to maximum 300 degrees Celsius, right? So you can reach from 25 you can maximum go to 300 degrees Celsius for this sphere. Above you cannot go because the surrounding gas itself is 300 degrees Celsius. Once you reach 300 degrees Celsius, there will be no heat transfer. Everywhere it will be same temperature, right? So the maximum delta T that you're going to give for this sphere is from 25 to 300. So then the total heat that you can store within the sphere is going to be simply mcp delta T, right? mcp. So the Q max is going to be simply mc into T initial minus T final. Here the T final is going to be simply the gas phase temperature, right? This is from initial you can go to only gas phase temperature, or maybe I should write this as a T final minus Ti because final temperature is higher. Okay, so the mass is nothing but we know it's going to be density times volume of the sphere. So I can write this as rho into V times C into Tf minus Ti. Okay. Now only 90% of this Q. So the actual Q is only 90% of this Q max. Okay. So once I reach 90%, I'm going to switch off. But I need to know at what time the 90% has been reached. Okay. That is our first problem. So the Q actual would be 0.9 times rho into V into C into Tf minus Ti, where Tf is, I can write this directly as Tgi minus Ti. Okay, this is something we will come back to this later. So now we need to perform a transient analysis. From 25 I want to reach some temperature, I don't know what is it till, but that will amount to only 90% of the Q. That is what we wanted to find. So how do we do it? So first maybe we need to see whether the lumped parameter approach is valid. Okay, so whether we can do lumped parameter is something you have to see before you start the lumped parameter approach. Okay, so if you want to see whether lumped parameter approach is valid, first you need to find out what is the Biot number. So the Biot number for this case would be h d by k. So basically it was, I think in the class what we did, Biot number is some characteristic length here. Here the characteristic length would be diameter simply, because that is our region of interest, right? H d by k. Now we already know h I think is 75 and d is 75 mm 10 power minus 3 divided by k, and k is 240 watt per meter Kelvin. So if you perform, you calculate Biot number and check whether it is coming below 0.1. and only if it comes below zero point 0.1, then lumped parameter approach is valid, and you go forward and apply the equations that you derived in the class. So this corresponds to something like 0.03, which is less than zero point 0.1. Therefore, lumped parameter approach is valid. Okay, so this is fine. So which means we can, basically you can do this calculation. So basically you can perform this. You can write your energy equation, energy balance like this, and then you change into theta, uh, and then you perform integration, apply the initial condition, you will end up having this. So maybe we will take from there. So what we are telling is, since this is a valid, I am going to say this theta is equal to theta I times e power minus t by tau, where tau is the time constant, which is nothing but a rho c v by h a, rho c v by h a. Okay, so what this tells is, um, we can always find temperature with respect to time. That is what, so this relation actually tells. But we are not interested in temperature with respect to time. We need to know heat transfer, right? Because we need to check how much time does it take to store 90% of the maximum thermal energy. So we somehow need to relate this to the heat transfer. Okay, how do we do it? So probably before we do it, let's find the time constant, which might be useful for us to simplify our calculation. The time constant, or you can say thermal response time, which will be rho c v by h into a. Okay, this a is the surface area across which the heat transfer is happening. Okay, which means for a sphere, the surface area, the surface area of the sphere is where the convective heat transfer is happening. So this a is going to be 4 pi r square or pi d square, right? So what happens if you write, volume of the sphere is going to be pi by 6 d cube, and h into area is pi d square. So if you simplify this thing, you will end up having rho c d by 6h. Okay, and I guess we know everything. Rho is 2700 for aluminum, and this is 950, and this is 75 into 10 power minus 3 divided by 6 into how much is the heat transfer coefficient? 75. That is also 75. So now if you put 75 here, the time constant comes out to be, if you guys find out, please let me know, 2700 times 950 times 75, 10 minus 3. So for me it comes out to be 427.5 seconds. Okay, this is the time constant. So what this actually means is, I don't know if you have uh, you know clearly understood in the class. So this is actually corresponds to uh, the time it takes for the sphere to reach 63.5% of the uh, the energy gradient that it was applied for. So for example, let's say, did I write it here? Okay, here it is not written. Okay, so basically, let's say when you apply a temperature gradient, uh, so now we have 25 and 300 degrees Celsius. Now to reach 63.5%, so of 25 minus 3 300 degrees Celsius, it takes 427.5 seconds. or you can say like half time, or close to half time, for the sphere to reach the 300 degrees Celsius would be around 427.5 seconds. So this just gives you a response time, or how much time does the sphere take in order to uh, detect the changes, the environmental changes it is feeling. Okay, how much time does it take, and how much time it takes to respond to the changes that it is uh, changes that's been imposed from the environment. So this gives you the idea of that. That's what this time constant actually means. Okay. So if you are very interested, please go through the books also, so that you will get a clear idea. So now we are doing this to simplify our analysis. So we can write this theta is equal to theta I times e power minus t by 427.5 seconds. Okay. Now we also know theta I. Theta I is nothing but t minus ti minus tgi, right? So actually it's t minus t infinity. Here the t infinity we are calling it as tgi, and theta I is nothing but the initial temperature. So that's why I took ti, which is going to be 25 minus 300, okay, which is minus 275 degree Celsius. So you can write theta to be, and what is theta? Theta is equal to t minus t infinity, where it is tgi. So you can write this as t minus tgi, which is again 300, is equal to theta I is minus 275 e power minus t by 427.5. Okay, so basically you can write this as t is equal to 300 minus 275 e power minus t by 427.5. So basically we have found the solution. There's nothing else. Okay, we actually found the solution with respect to time. So you plug in whatever the seconds, at what second, so let's say at 1 second, what is my temperature? If you want to know, you just substitute 1 here, you will get the temperature. Okay, or if you want to, let's say that at so how much time does it take to reach 200 degrees Celsius? Let's say if I want to know, you just substitute 200 here, rearrange this equation, this will give you t. Okay, it will give you time at which the temperature is 200 degrees Celsius. All these things you can find. Now this actually concludes the problem, but still we won't be able to answer our question. What is the time taken to store 90% of maximum thermal energy? That is something we need to answer. So till now we have been dealing with temperature, but if I want to know what is the energy stored, okay, uh, how would I do that, right? So one way is you have the maximum energy to be this. Okay, now you find out how the energy stored varies. Okay, which means, so basically if you remember, d by dt of energy within a control volume is nothing but E dot in minus E dot out, all these things we wrote, plus E dot generated. This is our energy balance, and we said there is no E in and E generated, and we have only E out, and we know E out is nothing but minus HAS T minus T infinity, or in this case it's TGI. So I want to know how this ECV, or in this case you can replace this with Q. I want to know how this Q varies with respect to time. How will I do it? Then you just integrate it to integral of HAS T minus T infinity dt. Okay, so now how much do I need to know? So initially I will be at 0, and I need it to be zero point 0.9 times Q max. Okay, and initially here we don't know, we know how temperature changes with respect to time. So here we are integrating with respect to sun, so we need to know 0 to t. So this time is what we are interested in finding. Okay, so now let's say this becomes simply Q, 0 times 0.9 q max is equal to h, and as is constant. T minus T infinity, we saw T minus T infinity is nothing but T minus TGI. So maybe I will use the same terminologies. TGI. Here also it's TGI. So T minus TGI is nothing but theta. This is nothing but theta, right? And theta we already know, it's theta I times e power minus t by 427.5. So let's say I substitute it here, theta I times e power minus t by 427.5 dt interval of 0 to t. Okay, so this corresponds to 0.9 times q max equal to h as. Theta I is also constant. You have integral of 0 to t e power minus t by 427.5 into dt. So you perform this integration. We know what is q max. What is q max? We found q max before. It's nothing but rho vc theta I, basically. Tf minus theta ti is, okay, let's write it down. Rho vc tf minus tg, sorry, what is tf? It's not tf, sorry, tgi minus ti. Tgi minus ti, which is equal to h as theta I. What happens to this integration? If you perform this integration, you will end up having e power minus t by 427.5, and you will substitute t, and then it becomes e power 0, so you will have 1 minus e power minus t by 427.5. Okay, this is what you will get. Now what you can do, this one and this one, if you look at this is nothing but minus theta I, right? This is nothing but minus theta I. This is theta I, and what is this one? Rho vc and has. So am I missing something? Rho vc and has. How where it is? Rho vc by h is nothing but tau. So let's rearrange this. This is 0.9 into rho vc divided by has into minus theta I equal to theta I to 1 minus e power minus t by 427.5. Okay, so this part we already know. So this part is nothing but tau. Okay, and this part is theta I, you can cancel. So what happens? Tau is, we already know, it's 427.5. Now you can write this as 0.9 into tau equal to 1 minus e power minus t by 427.5. So actually this is not right. If you look at it, you have the unit in the left hand side is actually seconds, but the unit here is not second, which means we performed some integration calculation mistake. So okay, so I think we forgot to, so this is nothing but e power minus t by tau, right? So ideally there should be one division by tau. right? So there will be divided by 1 by tau, which comes out to be tau here, which will have tau here. Okay, I forgot to do the integration carefully. So now you can see the units match. Okay, so this corresponds to 0.9 equal to 1 minus e power minus t by 427.5, and this will be e power minus t by 427.5 is equal to 0.1, then becomes minus t by 427.5 is equal to logarithm of 0.1, then t is equal to minus 427.5 into logarithm natural log of 0.1. So let's say if I calculate this one, natural log of 0.1 times 427.5 into minus this, t becomes 984 point, yeah, there's no point in this, 984 seconds. So this is the time it takes to store 90% of the maximum available thermal energy. That is what we did. We took energy balance. From energy balance we did this, but actually there is another way also. Let me tell you. So you can use your intuition. So this is your maximum heat, okay, and with respect to time, what can change is only this temperature can change, which means, you know, um, this is going to be like almost linear. Okay, how the temperature is going to change with respect to time, although it may not be linear because there is an exponential term, but uh, uh, but you will see for sure. Let's say if you consider the TF minus TI, it's 90% of uh, TF max minus TI. If you consider, then you can see, basically I'm telling, let's say you have like 275 degrees Celsius as a temperature difference between sphere and the air. Now if it is 90% of this 275, if that is the temperature difference that we are looking at, 275, which will be 247.5, for this temperature difference, how much time does it take? Or basically you can, go to this place, go to this place, and you can find this temperature from 90% of the total temperature difference, which will be how much? 275 times zero point 0.9, which is 247.5, plus initial was 20, initial temperature was 25, right? Initial temperature is 25, which is 272.5. If that is the temperature that we want to reach, then what would be the time? Okay, let's say if this temperature is 272.5, then what is the time it takes to reach this 272.5? If you find out, that might correspond to, that will be close to, what is the heat, 9, that will be close to 90% of the heat, maximum heat. Okay, let's see whether our hypothesis is right. So the second problem actually, revolves around that. The second problem says, what is the corresponding temperature at the center of the sphere? So at time t equal to 984 seconds, what is the t? T at 984 seconds, what is that? Is what they are asking. So we know t to be 300 minus 275 e power minus t by 427.5. So you just substitute it there. So 300 minus 275 e power minus 984 by 427.5. So this should probably correspond to our theory of 272.5. Okay, let's see. 984 divided by 427.5 and exponential of minus 2.3 times 275 300 minus this thing. So this corresponds to 272.477, which is almost equal to 272.5 degree Celsius. So this is indeed true, right? So for example, you are actually trying to heat the system from 25 to 300 degrees Celsius, and your heat is going to be uh, uniform. Okay, you are going to store the heat uniformly. Okay, so for example, if I want to draw this q with respect to time, initially I will have some lower q, which corresponds to 25 degrees Celsius, and I'm going to reach a higher q, which corresponds to q max. So this corresponds to 25 degrees Celsius, and this corresponds to 300 degrees Celsius. So this is how my heat is going to increase with respect to time, and I want to store 90% of it, which will be somewhere over here. So that is what basically we were trying to calculate. So this is one way to do it, but the more rigorous way is, so since here the specific heat is not varying with temperature, we no need to worry about it. We can say everything is constant, only delta T is varying. And if the delta T increases linearly, then our Q also increases linearly. But we have the exponent here, so which may not increase linearly. In this case it is close to linear, so that's why whatever our first order approximation was matching here, there it may not be close to linear, okay, in general. So that's why you need to perform a rigorous analysis like we did. You need to consider a heat balance and then perform the integration for the heat balance, substitute the temperature term, and then you perform this integration carefully. You will end up having temperature, sorry, time at which you will heat. You will get maximum uh, heat energy stored. Okay, all right, I hope this is clear. So finally the third one, it's mostly a conceptual problem. Yeah. Is there any advantage to using copper instead of aluminum? Okay, so what advantage do you think? Copper advantages. So I think we need to give uh, properties for it. I think K, rho and Cp is required. Rho is 8900 kg per meter cube, and Cp is 400 joules per kg Kelvin, and K, I don't think so we need it. So let's say for the same diameter, the diameter is changed same, so diameter is 75 mm. Now I have aluminum ball, this is copper. Okay, till now I have been using aluminum ball whose density was 2700 kg per meter cube, and Cp is 950 joules per kg Kelvin. So till now I have been using aluminum. Now I want to change it to copper. So what will happen if I change it to copper? The amount of heat content, how does it vary? Okay, the question is the Q, whether the Q stored by copper, maybe I'll write Q stored by copper is greater than, less than, or equal to Q stored by aluminum. So for a thermal energy storage system, what is the advantage? We want to increase the storage capacity of the system, and here the storage is done based on having these spherical balls. So if you increase the storage capacity of one ball that you have here, which means you can essentially improve the heat capacity of the entire storage system. Okay, that is what this means. So if you want to increase the storage capacity, so we already know the Q max, which is nothing but rho CV times theta I, right? Which is MCP delta T. Rho CV times theta I. Okay, this is basically MCP delta T. Now I'm telling I want to increase this Q max. So the advantage of a thermal energy system is to increase the Q max. I want to increase this Q max. One way I can do is I can increase the theta I. Okay, and the other way is I can increase the volume. So now let's say I cannot increase theta I cannot increase volume. I'm keeping the same diameter of the spherical ball, which means I cannot increase volume. And theta I is also, this is what is available. I can only have 300 degrees Celsius air to the inlet. Now if these two are not changing, but I want to change the Q max, then what you have to do, you have to change rho C. Okay, so just by changing rho, keeping C constant, you can still have improvement in Q max, but it is not possible. So there is no way you can find a uh, you know higher density material with the same Q, with the same C. So for example, you have C as 950 for aluminum and density as 2700. So you cannot increase just the density because it's a property of the system. So you cannot increase this. So you cannot change some other element such that it will give you the same C. Okay. So since rho and C are properties, you we are constrained by whatever is available. Unless you create your own, which is not possible. Unless you create your own element, it is not possible. So you have aluminum, which is 2700 and 950, which has you know uh, lesser density but higher specific heat compared to copper. Copper has higher density but low specific heat. So which means uh, not just the specific heat decides whether the Q is increased or decreased. It also depends upon the mass. Okay. For example, if you want to increase the Q max, the combined effect of rho C should be used to study the effect. So for example, let me write it down. So the rho C of copper is going to be 8900 times 400. So which will be 8900 times 400. So 3.56 into 10 power 6. Okay. Similarly, the rho C of aluminum will be 2700 times 950, which is 2.565 into 10 power 6. So now you can notice here, even though Cp has reduced, Cp is basically the storage capacity, heat capacity, right? Even though Cp has reduced, the total storage is can be increased because of the increased density. Because copper has increased density, it can have more mass within the system. And since you have more mass, even though its specific heat is less, it can store higher energy. That's what this means. So basically, so if you compare these two, the rho C of copper is greater than rho C of aluminum. Okay. So which means copper can store more energy for same diameter. That is important, for same diameter and the temperature theta i's than aluminum, even if its heat capacity is lower. Okay, so even though its heat capacity is lower, the amount of energy it can store is higher, because of sheer volume, sheer mass increase because of density. Okay, which means let's say I have a cube containing aluminum that will weigh less compared to cube containing copper. Okay, so which means the amount of mass in the amount of mass is more when you replace it with copper, and that is overpowering the CP decrease. Okay, so that is why you can say that I can replace with CP and I can get a better performance. For example, this will be, I think, around uh, around 40% rise compared to this. I think it's around 40% you can increase the heat energy. Roughly 40%. You can calculate it. How much is it? Roughly 40% thermal energy you can actually increase by replacing aluminum with copper. But what also increases, the total mass of the thermal energy system also increases. You can see from 2700 density you have went to 8900 density, right, which is thrice. So right, around thrice. 2700 into 3, more than thrice, right? um, More than 3 times you have increased the density, but you have reduced only like half time the specific heat. Okay, so which means 3 times your mass is going to increase for the thermal energy so storage system in the but the advantage you are going to get is only 40% rise in thermal energy. Okay, so that is something you should be careful. So it's just not the specific heat decides. It's not just specific heat decides. The combined uh, heat capacity decides. Okay, not the specific heat capacity decides. This is the heat capacity that it decides. Okay, it's a basic concept, but that is something uh, we can realize, especially in this transient analysis problem. Okay, all right. Any questions that you have? I hope there is no question. I think this is a new thing that we did here. I think professor didn't do the heat, how much heat, how the heat is varying with temperature, how the energy storage is varying with temperature. I think professor didn't do that. Right? Yeah. So that is something new that you might be seeing in this session. But I think this we usually used to do even in steady state heat conduction. If you want to know how the heat varies along the x direction, we may need to we will integrate and do things like that, right? So it's a similar thing. So basically, we get from the energy balance of the energy balance equation, and then we integrate it from zero. Initially, I will not store any energy. And then you want to go till 0.9 times Q max, and once you go that, you will end up having this, and then it's just pure integration and some cancellation arithmetics, and then you will end up having the time. Okay, so rather than using this, you are using a little bit complicated expression of this. That's it. All right, any questions? All right, thank you, Avinash. If there are no questions, um, then thanks for attending, and we'll meet next week. Thank you, Avinash. We'll meet next week. Bye bye. I will be anyway staying for a couple more minutes. If anyone wants to join and ask any questions, I will be available. Uh, but you can leave if you are